We are introducing our work on safety of automated driving. More specifically, we establish mathematical proofs for its safety. Automated driving is one of the most promising future technologies that will change the world. However, its real-world development has not been as smooth as expected. Besides technical challenges such as perception and control, one major challenge is the problem of safety assurance and social acceptance. Autonomous vehicles must be safe enough to be accepted on public roads, and society must be convinced of their safety by rigorous guarantee and extensive explanations. Safety guarantees for automated driving are commonly given in two ways: by statistical data and by testing with computer simulators. These are important methods of safety guarantee. However, there are possible major criticisms of these empirical guarantees. One is whether the guarantees are strong enough. Statistical analyses produce average numbers, such as 9.1 crashes per million miles driven, but they do not rule out the possibility of your car being doomed to always crash at a specific intersection. In testing with simulators, one has to argue that every important driving scenario is included in the test, but this is hard. Another possible criticism is explainability. These empirical methods only give numbers, while the society and the public typically want logical explanations as to why the car is safe enough. Therefore, people have turned to mathematical proofs as an ultimate method of safety guarantee. For one thing, mathematical proofs give very strong guarantees. Once we prove something as a theorem, it simply cannot be wrong. For another, mathematical proofs offer strong explainability. They are detailed descriptions of the logical reasoning steps that lead to safety guarantees. Customers, regulators, auditors, and the public can trace these logical steps to understand why an automated driving car is safe. However, autonomous vehicles and their driving environments are highly complex systems with enormous uncertainties. These uncertainties make fully mathematical safety proofs extremely difficult. Here is a methodology introduced by researchers at Intel Mobileye that makes safety proofs for automated driving possible. It is called Responsibility Sensitive Safety, RSS in short. The key is to split the whole safety argument into two parts. The first part is a mathematical one, where one proves that compliance with so-called RSS rules guarantees that no collisions occur. The second part argues that cars indeed comply with RSS rules. This second part should be guaranteed by the car's manufacturers at their discretion, and does not necessarily rely on mathematical proofs. Combining these two parts, as a logical consequence, one argues that there is no collision. Each RSS rule is specific to an individual driving scenario. Here is an example of an RSS rule for a single-lane, same-direction scenario. It stipulates that the subject vehicle must maintain a minimum safety distance to the lead vehicle. Note that the RSS rule gives a precise condition in the form of a mathematical formula whose safety can thus be formally proved. Note also that the condition is checkable. Indeed, it only refers to the current situation rather than future ones. The driving scenario in the last example was quite simple. In fact, RSS has not yet been applied to complex driving scenarios like this pullover one shown here, where we have to consider sequences of maneuvers and their interdependencies. In our work, we propose the first formal logic system for RSS. Together with the software support that we also developed, we can now apply RSS to complex scenarios. In particular, thanks to our logic system, our RSS rules can guarantee not only collision freedom, but also goal achievement, such as successful pullover in this scenario. We call this extension Goal-Aware RSS, GA-RSS. We believe it is a crucial extension to the real-world adoption of the methodology of RSS. Our results on the logical foundations of RSS enable the transition from informal pen and paper proofs to formal software-assisted proofs. Pen and paper proofs are error-prone and do not scale well. Their traceability is poor, too, when it comes to auditing by other parties. In contrast, our formal logic system DFHL enables writing proofs using software. The complex manipulation of mathematical formulas can thereby be conducted by a computer. Moreover, software can check the validity of each logical step in a proof. To demonstrate the power of our GA-RSS extension, we're going to use this pullover scenario as an example. Now we will compare the performance of three controllers controlling this green vehicle in a pullover scenario. The goal is to reach a designated yellow zone in the leftmost lane that is not yet visible. The first controller has no safety module at all. It immediately cuts in front of this blue car at an unsafe distance, represented by the red zone. This is a severe violation of the RSS safety distance. If the green car had to suddenly brake, the blue car would not be able to stop in time and a collision would occur. Let's compare this behavior to that of a controller with a classic RSS safety module. In this case, the safety module can take control to rectify an unsafe behavior of the underlying controller. This is indicated by the car turning light green. As in the first simulation, the underlying controller tries to cut in, but now the safety module repeatedly takes control to avoid this. In the end, the yellow goal zone is missed. Now we turn to our contribution, a controller equipped with a goal-aware RSS safety module. At first, it behaved like the previous controller. Its attempts to cut in front of the blue car are repeatedly blocked by the safety module. At this point, the green car must start braking in order to merge behind the blue car, since there is no safe way to reach the goal which merges in front of it. The goal-aware module therefore takes control, since otherwise its safety condition would be violated. Finally, the target zone is reached safely.